So, not to be foolhardy, let's do a 1D. It is depending where you start, when you start counting one-dimensional fluid dynamics. It's actually essential to this. Same thing is true of, let's say, general relativity. For space-time dimension, it gets really interesting. There are three-dimensional, two-dimensional versions. They're quite different. So, but there is a set of equations that show up very often in application and applied math, which look like this. In particular, what we'll do is we'll study a ring of fire. It's a perfect ring. In that case, it's called Bunsen-Burner. That's what chemists use. And and for slow velocity, this will be stable. There will be just a ring of fire of equal height where the gas meets oxygen and burns. And as you turn it up, it'll start fluttering. So that's the simplest example of turbulence. It's one-dimensional rather than three-dimensional. It is still about velocity, how thing moves. And several people have written phenomenological equations to describe it. And what happens in one dimension, u vector becomes u. And if you have a gradient, that just becomes derivative with respect to the single spatial. And the simplest such equation that there is a large community standard, we will call the ring of fire after Johnny Cash. This is a misattribution. Before Johnny Cash described it, and physicists, and it looks like this. It has a time derivative, so now subscript will indicate derivative. It has this gradient term, and the square of the function, if I expand it, it'll look exactly like that. It'll be just in one dimension. Then there'll be no pressure, but there will be a Laplacian of this form. It turns out it's a weird. So what actually, when you look at this, what actually its term will do, it'll put the energies. So this term will actually play the role of forcing of dynamical system. So it says, if our wavefront is wavy, this will try to make it wavier. This will try to amplify it. Now that would be bad news. Things would explode. So then there is an extra term called hyperviscosity. It has this coefficient, but it's not Laplacian. It happens to be Laplacian square. And these Laplacian squares, they're not so strange as they might be in theory of continuous media, shells, etc. So what it is we are looking at a field. Now it's defined in one dimension. Only this is defined on configuration space, which is one-dimensional, and it has a perimeter, and it's periodic, meaning that ux of t at any instant in time is same as x shifted one time around the perimeter at the same time. So, periodic BCs. It's not essential, but it's convenient. What periodic boundary condition, the world is equally distant, because you have to go all the way around half of the perimeter before you start noticing that you are on a compact domain and not on the. And it turns out when we do computations with Navier-Stokes, we are forced to, so it's not so far away for we have to do when we actually do computations with the problem that we care about.
Love is a burning thing, and it makes a fiery ring, bound by what desire. I fell into a ring of fire.